Good afternoon, my name is Christopher Meert, and I'll be talking to you today about the detection of fast neutrons during photon active interrogation. This will be a highlight PowerPoint slide set of my poster. I'd like to start out by acknowledging the other collaborators in this project, including Abbas Jinnah, Andrew Panter, Aaron McDonald, Dr. Hyunsuk Kim, Dr. Sean Clark, Professor David Wensloff, and Professor Sarah Potze. I would also like to acknowledge the funders of this work, including the Department of Homeland Security through the Countering Weapons of Mass Destruction Office and the Consortium for Monitoring Technology and Verification. We are interested in developing new active interrogation systems because they have the capability to detect shielded special nuclear material, say in the case of highly enriched uranium, which emits relatively few passive radiation signatures. If we're able to increase the deployability of these systems, we can improve our overall capability to interdict illicit special nuclear material. Therefore, the goal of this project is really to develop some high-confidence techniques to detect prompt neutron signatures during photon active interrogation. So here's a quick methodology overview for the experiments we conduct. This is an overhead view of our lab space. You can see on the left there is a LINAC inside of a shielding vault that's going to emit our photon beam, which will be collimated, and irradiate our DU target, shown in the yellow. It's going to emit our photoneutrons, which will then be detected by various detectors, shown in that white location there, either Helium-3, Helium-4, or StillBe. First up, let's summarize the results from the Helium-3 detectors. Helium-3 is often used as a neutron detector because it has high efficiency. However, these are proportional counters, so the detector pulses will be on the order of 10 microseconds, which is long compared to the LINAC, which will emit photons in 4 microsecond bursts. On the right of this slide, you see the pulse integral spectra from two scenarios: blue for DU interrogation, pink for the active background. Active background is where we run the LINAC, detect neutrons, but we have no irradiation target. We do still observe neutrons. That comes from the lead in the collimation and beam stop, which can undergo photonuclear reactions and produce neutrons. Still, we see a substantial increase in neutron counts when we add the DU, which is a great sign. In the spectra, we see typical helium-3 response, including the helium-NP reaction, a fast neutron scatter continuum, but also a pileup region. We integrate that peak in the pileup region, we arrive at a count rate of about 45 Hz, and that is identical to the LINAC repetition rate. So we're probably still detecting neutrons in between our LINAC pulses, but each time the LINAC fires, this helium-3 detector is getting blinded by the intense radiation field. The second piece of results I'd like to highlight are from the StillBe detectors. On the top two plots, you see results from a 2-inch StillBe measurement while interrogating depleted uranium. On the bottom, the 6mm StillBe results during DU interrogation. These PSD plots show the tail to total ratio as a function of the total integral. You can see red lines on each of the plots which correspond to the discrimination line. In general, pulses that appear above the discrimination line are identified as neutrons, those below are photons. The difference in each pair of plots is the application of pileup cleaning. So on the left, we clear out clipped pulses or noise pulses, but no pileup pulses. The pulses on the right include clipped cleaning, noise cleaning, and pileup cleaning. And so we notice in the upper left plot that there are a lot of pileups recorded in the 2-inch StillBe result. That's very challenging because that's also where we expect many of the neutron signals to arrive. When we apply the pileup cleaning, many pulses are rejected for analysis, and we can't even see a defined neutron band. If we reduce our overall detector size, the plots on the bottom result, here we see an overall decrease in total detection events, which is expected because the volume is being reduced, and therefore our detection efficiency is being reduced. However, we see much fewer pileups, and when we apply cleaning, we still see some neutron pulses that are in the region that we expect. They still appear where that neutron band ought to appear. This is a good result because it shows that by reducing our overall detection efficiency, we're actually getting higher confidence results. Perhaps fewer total pulses, but the pulses that we do record appear to be clean single pulses, which can then be classified accurately as neutrons or photons. So in this work, we've tested several detection techniques for photon active interrogation. However, StillBe continues to be the most effective detector for these applications. It has very fast time response, and its pulse lengths are on the orders of nanoseconds as opposed to microseconds. And it has the ability to detect both photons and neutrons. From our StillBe results, we see that a detector optimization is certainly worth exploring. Even though we reduced detector size, which does negatively impact detection efficiency, we're also reducing pilot, which can result in higher confidence results. And so our next steps include a detector optimization, comparison with neutron activation foils, and some analysis with machine learning-based algorithms. You can see additional information for those topics on Poster20 presented by Andrew, and Poster19 presented by Tessa. Thanks for listening to my talk.